All right, so today we border on abstract algebra. This is as close to abstract algebra as we get. We take a look at the set of Euclidean isometries and we see how they play together. I start out with a few lemmas that might be helpful, and then you go to work mostly in the discussion. So this is Lemma 10.3.3. It's got a very catchy name. We assume that L, M, and N are three lines concurrent at P. Then there exists a line S such that P lies on S, and the reflections in L composed with a reflection in M composed with a reflection in N is the same as a reflection in just S. So here's point P. L, M, and N are concurrent at P, which means this. L, M, N, all concurrent at P. We must prove that there exists a line S such that P lies on S, and this composition of reflections is the same as just one reflection. Three reflections is one reflection. I propose that this is the S that we need. So here's the idea. We apply the rotation theorem to conclude the existence of S, there's S, such that this composition is the same as this composition. Now, how do we get away with that? Well, there's some angle between L and M. We can make a line S at the same angle to N through P. So whatever this angle measure is, we can measure it, and then protractor postulate says pick the half plane, pick one half plane bounded by N, construct this angle to be the same. So there is a line S such that this holds. Well, yeah, well, that's great. That gets me 2/3 of the way to what I want, right? What I want is this. And so you can't just tack on a composed with on one side without tacking on a composed with on the other side. Well, what happens when you compose a reflection in line N with a reflection in line N? You end up right back where you started. And so sure enough, the line S that we need is the line that does this, because then this thing that we want is just a single reflection. So what's the key to the lemma? If I have three lines concurrent at one point, and I want to reflect over all three of them, I can replace these three lines with one line, and a reflection will do the same thing. A single reflection does the work of three if those three lines are concurrent. The other lemma we should play with is this one, and this is just a doozy. So we assume that there's a line L and a line M, and L and M intersect maybe at A. You have this other line N sort of off over here like this. Maybe N is parallel to M, maybe N is parallel to L. It doesn't matter. The key is that L and M intersect. We want to show that reflecting in N, then M, then L is a glide reflection. So L and M intersect, so there is some point A on L and M. We let S be the line perpendicular to N through A. This is line S. By the rotation theorem, there exists a T such that this reflection that we want to do away with is the same as this reflection that we'd like to keep around. So again, whatever angle this is, we construct it over here, and then this becomes line T. M then L is S then T for this very reason. So therefore, reflecting in L composed with reflecting in M composed with reflecting in N is reflecting in T composed with reflecting in S composed with reflecting in N. So we're going to let B be the point where S and N come together. And then we're going to think to ourselves, drop the perpendicular to T through B. This line, perpendicular to T through B, this is going to be line K. And that foot is going to be C. And then we're going to take H to be the line through B that's perpendicular to K. So here's line H. They are perpendicular, H and K are. Here's the funny thing about that. S and N are perpendicular lines. H and K are perpendicular lines. S and N pass through point B. H and K pass through point B. By the half-turn theorem, it doesn't matter if I use S and N or H and K, they are the same. So reflection in L composed with reflection in M composed with reflection in N is reflection in T composed with reflection in H composed with reflection in K. Half-turn theorem says it doesn't matter which two perpendicular lines I choose at B, they do the same thing. Now, what do we notice about line T and line H? Well, line T and line H, this composition is a translation along K, because these two lines are both perpendicular to the same line. So reflecting over two lines that emit a common perpendicular is a translation along line K. So what is this? This is a translation along the vector of a reflection line composed with a reflection. So this is a glide reflection as needed. So when we have three lines, two of which intersect, the composition of the three of them is a glide reflection. And that's an important thing to remember. Okay, those are a couple of lemmas that'll help us with the setup for what comes next, and that's super important.